All right, this is a continuation of the 6.2 notes that we were on class. We needed to look at example 3, find the values of the trig functions that correspond to theta. And these were for our special angles, 30, 60, and 45. We did 60 and 45 degrees in class. We want to make sure we know how to do the ratios for 30 degrees, and then there'll be a summary chart on that. So remember, we learned in class that the way, and this is a horrible drawing, but the way they figured out the 30, 60, 90 triangles ratios is they took an equilateral triangle with all the sides being 1. And notice that if it's equilateral, that means all of the angles are 60 degrees, but this is cutting this in half, so that was 30 degrees on each side. And since this is 1 on all 3 sides, when you cut it with that perpendicular bisector, this actually makes this 1/2. And then we used Pythagorean theorem to find out that this was square root of 3 over 2. So that's already in your notes. But now we're looking at a reference angle of 30. So this would be opposite, this would be adjacent, and this is still the height of that triangle. So sine of 30 degrees is opposite over hypotenuse. So that is 1/2 over 1, which is just 1/2. Cosine of 30 degrees is adjacent over height. So that's square root of 3 over 2 all over 1. So that's just square root of 3 over 2. Tangent of 30 degrees is opposite over adjacent. And then we would take this and multiply top and bottom by 2. We get 1 over the square root of 3, and then we would rationalize that. So that is square root of 3 over 3. Remember, then we can find our reciprocal ones. So cosecant of 30 degrees is just this one flipped, so sine flipped, would just be 2. Secant would be 2 over the square root of 3. And if we rationalize that, that would be 2 over the square root of 2 on the square root of 3 over 3. And then finally, the cotangent, it's easier if you just flip this before you rationalized it. So it was 1 over square root of 3, so it's just going to be square root of 3. Now, the most important of those are sine, cosine, and tangent. If you look at this chart right here, it tells you the special values of the trig functions. They also give you the radian measure that matches this. So 30 degrees is pi over 6, 45 degrees is pi over 4, and 60 degrees is pi over 3. Notice that the sine and cosine of the pi over 6 and pi over 3, or 30 and 60, they're just flip-flopping because they come from the same triangle. You're just referencing a different angle. But notice that sine and cosine are exactly the same in a 45, 45, 90. So let's look at our first example here. This is assuming that A is 10, and we're going to look at what are X and Y. So right now we have opposite, and this would be height, and this would be adjacent. So we could do, since opposite and height, I could find X. Opposite and height makes sine. So sine of 60 degrees would equal opposite, which is 10, over height, which is X. If we figure out what sine of 60 is, which remember is up here, so 60 degrees sine is square root of 3 over 2. And you'll get better with these, and you almost always have them memorized once we get going. So sine of 60 degrees is square root of 3 over 2. Then we can cross multiply, so this would be 20 from 2 times 10 equals square root of 3 times X. And we would divide both sides by square root of 3. So 20 square root of 3 needs to be rationalized. So 20 divided by square root of 3 is 20 square root of 3 all over 3. So that's going to be my height. Now I could try to do Pythagorean theorem to find this other one, or I could just try to do 10 and y as a relationship to 60, which is tan. So either way should work. Oh, excuse me. So if we did tan of 60 degrees, that would equal opposite over adjacent. So 10 over y. And tangent of 60 degrees is just square root of 3. So think of that as over 1. We can cross multiply and then divide by square root of 3 again. And then when we rationalize, that would be 10 on the square root of 3 over 3 by multiplying top and bottom by square root of 3. So then this final side right here is 10 square root of 3 over 3. Which makes sense because remember the 30-degree angle is half of the hypotenuse. So 20 square root of 3 over 3, and this is 10 square root of 3 over 3. Okay, for the B part, we have that S is 14. Now, because this is a 45, 45, 90, X and Y are equal to each other because of the two matching angles. And we know this matches because a triangle has to add up to 180 degrees. So we can just try to do one solving essentially. So if we use, this is op, this is hype. So sine of 45 degrees equals opposite over hype. Sine of 45 degrees is square root of 2 over 2. Cross multiply, so 14 square root of 2 equals 2x. Divide by 2, and we get that x equals 7 on the square root of 2. That's also our y, so both of these are 7 on the square root of 2. I wrote 3 somehow. There we go. No, it's a 2. Okay. We did example 5 at the end of class last time, so let's look at example 6. The peak of Mount Fuji is in Japan, and it's approximately 12,400 feet high. So here's the mountain, and we say that the height of that mountain to the top peak is 12,400. A trig student is several miles away, so we don't know how many miles, but several miles away. And they are looking at an angle up at the peak from the ground level. And their angle is 30 degrees. Estimate the distance from the student to the on level ground directly beneath the peak. So we're looking for this distance here. So this is opposite to the angle that we have. This is adjacent, so we're going to have to use tangent. So tangent of 30 degrees equals opposite over adjacent. We could try to cross multiply right now. That would be tan 30 degrees times x. So you don't always have to convert the tangent first. I'm going to show you that you can do this one too with your calculator since they said to round. So we're going to end up dividing both sides by tan of 30 degrees. Now when using your calculator, you want to make sure that you are in the correct notation for using it for angles. There is both degree and radians, so you have to know how to change between them. It usually defaults to degrees, but always double check. So 12,400 divided by, and mine is in degrees, so 30 tan, and most of calculators you'd have to enter the tan first. And then I hit enter, that's 21,477.4 because it does say it around a 1 decimal place. So 21,477.4. And that is feet away, or sorry, miles. Actually, this would be in feet because the original height was in feet. I mean, you could divide and figure out how many miles that is away. It's going to be a little bit over 4. So there we have that. All right, so the last thing that I'm going to do on the video, because there's a lot of things, at least this part 1 is going to end after fundamental identities. So after we do these examples, I'll be cutting this video off and I'll be making a secondary video hopefully tomorrow morning when I'm a little bit less tired. Fundamental identities are those that are true for every acute angle theta, and theta may take on various forms. So later we're going to see that these identities are also true for other angles and for real numbers. So we already knew that the reciprocals existed, but this is their property. Cosecant is 1 over sine theta. Secant theta is 1 over cosine. And cotangent theta is 1 over tangent, so it's the reciprocal. This is a breakdown of how tangent and cotangent are split into pieces. Tangent theta is sine theta over cosine theta. So remember, opposite over adjacent kind of thing. And cotangent theta is cosine over sine theta. So notice it's a flip-flop. A squared plus b squared equals c squared is really important for us. And the Pythagorean identities for trig are sine squared plus cosine squared equals 1. And those are both thetas, by the way. And then these two are found by taking this and dividing it either by sine squared or cosine squared. So let me show you for a minute how you just really need to memorize this one if you're like struggling to memorize a lot of things, because you can recreate these two. So if you have sine squared theta plus cosine squared theta equals 1, and you divide everything by sine squared. Theta. Okay, sine over sine, since they're both squared, that's just going to be 1. Cosine squared over sine squared is cotangent, because that's cosine over sine, and it'll be squared, since there were 2 of them. So this would be cotangent squared theta. And 1 divided by sine squared theta is cosecant squared theta. So notice that's this third one over here. To get the middle one, you just divide everything in the original by cosine squared theta. So that's just interesting to note. Okay, so this first one says, let theta be an acute angle and express tan theta in terms of cosine. Well, the first thing I would think to do is to write it as sine theta over cosine theta. And I'm thinking, okay, well that's good because I have a cosine there. The problem is we need to somehow get rid of the sine and write it as a term, or maybe a binomial or trinomial of terms, depending on what it is, that are only in cosine. So if we take our very special sine squared theta plus cosine squared theta equals 1, if we solve that for sine, we will have something that's in terms of cosine. So I'm going to move the cosine squared over by subtracting it. And then because this is squared, I'm going to take a square root. The reason I can take a square root over here is because this is isolated and it's being squared. So this is just now sine theta. On this side, you can't take the square root of both of these because it's a binomial. So this is just 1 minus cosine squared theta. So then my final answer for this one is I have 1 minus cosine squared theta all over cosine theta. Notice now tangent has been written using only cosines. Similar exploration for this one, we want sine theta to be in terms of cotangent theta. So sine theta, remember, is 1 over cosecant theta using our reciprocal property. And then we do have a Pythagorean identity, remember, that uses cotangent and cosecant squared. So I'm going to write it down here. So 1 plus cotangent squared theta equals cosecant squared theta. Notice that we just have to take the square root to get that, or excuse me, that's supposed to be, yeah. We just need to take the square root of this to make this solve for cosecant so we can replace it. So this would be square root of 1 plus cotangent squared theta equals cosecant squared theta, or excuse me, just theta, no square anymore. And then this would replace the cosecant. So 1 over the square root of 1 plus cotangent squared theta. And again, you can't cancel out that square root because it's connected as a binomial in the bottom. And we're not going to make you rationalize that one when we're just trying to convert. Fundamental identities are often used to simplify expressions using trig functions, as illustrated by this next example. So we're going to use our Pythagorean identities to write an expression as an integer. So this is just, if you want to think of it, if theta is 8 beta, so that we don't really get confused by that 8 part there. Then this is tan squared theta minus secant squared theta. Okay, so that's not a property that we had directly, but if we look back, we had 1 plus tan squared theta equals secant squared theta. So 1 plus tan squared theta equals secant squared theta. So it looks like we want to move the 1 over and then the secant squared over. So if we leave tan squared where it is, but we move the other two pieces, we get that tan squared theta minus secant squared theta is -1. So this actually equals -1. The 8b part, or 8 beta inside, does nothing. It's actually our theta. That is very different than what's going on in B. Think of B as having an 8 out front. It actually does have it out front. You can pull that out to the beginning because both of them have it. Let's look at our little theorem for this one. It looks like cosecant squared, if we subtract over the cotangent squared, is going to equal +1. That's just from our identity up there. So this is 8 times +1, since the 8 was out front, which equals 8. For this one, you have two things going on. The theta over 4 really doesn't affect anything just because it's the theta for our problem, but the 5 out front could be pulled out. So we have 5 times sine squared of theta over 4 plus cosine squared of theta over 4. And notice that sine squared plus cosine squared is always 1. So this is 5 times 1, which is 5. Okay, just two more examples. So example 9 says, show that the following equation is an identity by transforming the left side into the right side. We can't do anything like moving stuff from left to right. You don't do that with these. What we're going to do is take this side and somehow make it look like the other side. So the first thing that's usually a helpful thing to do is to try to convert everything to sines and cosines. So secant theta, remember, is 1 over cosine theta, plus tangent theta is sine theta over cosine theta. So that's already helpful because now those have a common denominator. And then this would be 1 minus sine theta. And then on this one, we combine those, and that's 1 plus sine theta over cosine theta. And that's 1 minus sine theta still. We would then just, this is over 1, so we would distribute the top. That's 1 minus sine theta plus sine theta minus sine theta, squared theta. The sines are going to cancel on top, and we still have our cosine in the bottom. And then you get 1 minus sine squared theta on the top. Now, a lot of times things go back to the Pythagorean theorem, or the identities, I should say, which was sine squared theta plus cosine squared theta equals 1. If you subtract over that sine squared theta, you get 1 minus sine squared theta, which is our numerator, is actually cosine squared. And that's going to be how we're going to get it down to just cosine. Because a square on there actually means cosine times cosine theta, so it's both of them. So one of these can cancel with one of those, so we just get cosine theta. Okay, for example 10, this one's a little trickier because it requires you to remember how to factor something that has perfect cubes. And I'm going to show you with x and y because that's always easier than sine and cosine. So remember, if you have two perfect cubes with a plus sign in between them, you write the cubed root of each one, which would be x and y, with the same sign, and a binomial. Then you have a trinomial where you take the roots, which were x and y, and you pair them in different ways. So x times itself, which would be x squared, x times y, which would be xy, and then y times y, which would be y squared. If you've done that correctly, you should have something that looks like this. And then the sign is always same as the original for the binomial, opposite to the original for the first part of the trinomial, and then always positive. We remember that by SOAP. Same, opposite, always positive. So notice this is the same exact thing, except this x is a sine and the cosine is the y. So this would be sine theta plus cosine theta times sine times itself would be sine squared. And then in the middle, we would get a minus sine theta cosine theta. And then plus cosine squared theta. So what we end up seeing is that we have that's on the top, and the bottom is just sine theta plus cosine theta. So that's going to cancel with that first part. We have a sine squared and plus a cosine squared. That's actually a 1. So on top, we have 1. And then minus sine theta cosine theta. Okay, that's it for part 1 of the video. Hopefully I can have some time tomorrow to make part 2 and get that published for you guys.